And we're back. And this is going to be the 16.2 lecture for concentration of solutions. And so we're going to start by establishing the definition of concentration. Concentration is the amount of solute in a given amount of solvent or solution. It's just how much is in there. Okay, for a given amount of solution. And we use four types of concentrations in chemistry, in our chemistry class. We use grams per liter, which is really pretty straightforward. Molarity, which has to do with moles. Parts per million, which seems pretty straightforward, and it is, but it's a new form that maybe you haven't heard of before. And then percent composition. Okay, and before we go on, what I want you guys to be able to do, or what I want you guys to do, is to rank, once we finish the section, rank from easiest to hardest the concentration calculations covered in this section. There is no right or wrong answer for this. These are what are easy or hard for you, so we can identify what we need to work on in the future. So we're going to start with grams per liter solution. This is often used for aqueous solutions, where the solute is a solid. So we're going to calculate the grams per liter when 35.0 grams of sodium chloride is dissolved to make 425 milliliters of solution. So the key here is to convert milliliters to liters by dividing by 1,000. And it works like this. So we have 35 grams. We're going to divide it, so it's always a solute over solvent, and then we convert it to the units we want. So 35.0 grams divided by 425 milliliters. But then we need to multiply by 1,000 milliliters per liter to give us our 82.4 grams per liter. Okay, so remember, there's 1,000 milliliters per gram, 1,000 milliliters per liter, and 425 milliliters on the bottom. That would be the solvent. Solute over solvent. Okay. Now, it could also be over solution, amount of solution as well, and that's what we're going to get to with molarity, which is the next one. Molarity is merely the number of moles of solute per liter of solution. There it is. There's a solution in the bottom. That's the number of moles of solute per liter solution. So we're going to calculate the molarity of a solution when 10 grams of sodium hydroxide are added to enough water to make 100 milliliters of solution. All right, so 10 grams. This is not moles. This is in grams. So we are going to need to convert to moles. And this is how we do it. We take 10 grams and we divide it by our solvent. So it's always solute over solution, solute over solution. And we need to convert these. We have two different conversions we have to do. We have to convert this to moles per liter. So we're going to start with converting to liters. So we're going to have 100 milliliters, where we know that 1,000 milliliters equals 1 liter. So those will cancel, giving us 1 liter on the bottom. But then we need to convert our grams of sodium hydroxide to moles. So we have 10 grams of sodium hydroxide. And we know that 40 grams, remember 23 plus 16 plus 1, NK plus O plus H is going to give us 40 grams per mole. 40 goes on the bottom, 1 mole goes on the top, and all of a sudden we are left with grams in any way cancel. We are left with moles over liters. Moles per liter, and that's 2.5 molar. This is called molar solution. 2.5 molar solution, or 2.5 moles per liter. Let's try another one. How many grams of NaCl then how many grams of NaCl would be needed to make 400 milliliters of a 0.6 molar NaCl solution? So The hint is going to be we're going to start with the volume, which is 400 milliliters, and then use the molarity as a conversion factor, because molarity, big M, equals moles per liter. So we know that there's so many moles in every liter. If we have 400 milliliters, we can figure out how many moles we have. So that works like this. That if we have 400 milliliters over 1, because some of you guys need that, divided by 1,000 milliliters is going to give us 1 liter. Right? But we don't want liters. We want grams as our target. So we need to convert this over to grams. 400 milliliters divided by 1,000 milliliters per liter. And we're going to multiply that by 1 liter equaling 0.6 moles of NaCl. But we know that 1 mole of NaCl is 58 grams of NaCl. And so we multiply across the top, we divide by everything on the bottom, and we're going to get 14.04 grams of sodium chloride. Okay, so go ahead and rewind that and play it again if you didn't miss it, if you didn't catch it the first time. That's why it's the magic of video. Okay, which brings us 2 parts per million. That is ppm. ppm is 1 part solute by mass per million parts solvent by mass. However, the density of water is already 1 kilogram per 1 liter, but 1 kilogram of water is 1,000 grams, okay, or 1,000 milligrams. So 1,000 milligrams of water equals 1 liter of water. This allows us to find, this turns out to be, as we go to the next page here, this winds up being, for parts per million, in an aqueous solution in particular, is number of milligrams of solute per liters of water, because that's also the milligrams of solute over 1 million milligrams of water. But remember, this million milligrams of water equals 1 liter of water. So milligrams per liter is the same thing as parts per million. So here's our sample problem. Calculate the ppm in a solution containing 2.5 grams of salt. We're going to convert that to milligrams, remember, in 650 milliliters of water. Well, 2.5 grams of salt is going to be 2,500 milligrams of salt, and 650 milliliters of water is 0.650 liters of water. Therefore, 250 milligrams of salt in 0.650 liters will give us 3,800 parts per million NaCl. So if we do another one, calculate the number of grams of chloride gas needed to mix with 500 milliliters of water, make it 400 parts per million. We do the same thing as the molarity problem on the previous one. The 400 parts per million is our conversion factor. So we're going to multiply our 500 milliliters of water by 400 ppm after we convert it to liters. So 500 milliliters, okay, divided by 1,000 is going to give us our liters. But we know that 1 liter equals 400 milligrams of chloride. And 1,000 milligrams of chloride equals 1 gram. So we get milligrams of chloride, so it's 1 gram of chloride, and that gives us 0.2 grams of Cl2. Again, if you are losing the calculations, go back, track where everything comes from, using the magic of video. Okay. And then finally we have percent composition, which is a mass ratio of the grams of solute or solvent to the total grams of solution. The basic formula for it is this. It's the mass of solute or solvent, however much you have, okay, divided by the mass of solution, times 100 will give you your percent. Or It's the part that you're looking for divided by the whole times 100, and that gives you a percent. Our sample problem is calculate the percent composition of glucose in a solution made by dissolving 45 grams of glucose in 650 grams of water. Well, the total mass of the solution, once the sugar is put into the water, is going to be the 45 grams of glucose plus the 650 grams of water makes 695 grams of solution. Therefore, we're going to have 45 grams of glucose and 695 grams of solution, which gives us 6.47% by mass. Now, of course, this fraction here doesn't equal 6.47, it equals 0.0647. But then you multiply by 100 and you move the decimal back twice to give you 6.47. Okay, so the next one is we're going to calculate the mass of NaCl needed to make 500 grams of solution that is 8.5% sodium chloride. 8.5% is going to be our conversion factor again. So we know that the part equals the percent times the whole over 100. So 8.5% times 500 grams divided by 100 is going to give us 42.5 grams. So let's work this out. So let's calculate. So this is going to be 0.5 times 500 divided by 100 equals our 42.5 grams of NaCl. That would be our 8.5% of all of the solution. Okay, so let's try one more of those. We're going to calculate the mass in sterling silver that could be made by mixing 40 grams of silver with copper. Now, sterling silver is 92.5% silver and 7.5% copper. So, if we have 40 grams of silver, and we know that that equals 92.5% of it, so we can do a proportion here even. So that 40.0 grams is to 92.5 as X is to 100%. That's one way of doing it. So this is going to give us 40 times 100 divided by 92.5, which is exactly what we have over here. And that will equal 43.2 grams. And that's going to be the total mass of sterling silver that we could produce from an original stock of 40 grams of sterling silver. Which brings us to the dilution problem. We are going to use the formula when we do a dilution problem. M1V1 equals M2V2. Okay, the formula is M1V1 equals M2V2. Now, if you have any kind of physics background, that's also the same thing for the conservation of momentum. However, that is not what we're doing in this particular case. In this case, M1 and M2 are the molarities of the solution, and V1 and V2 are the volumes of the solution. And the cool thing is, as long as you're consistent with your molarities and your volumes, units don't really matter. So, for example, we want to calculate the volume of concentrated hydrochloric acid needed to make 500 milliliters of a 3 molar solution. Also, how much of the 12 molar, so M1 is going to be 12 molar, because that's what we're starting with. But we don't know how much of that we need. But we want to make a second molarity of 3.0 molar and we want 500 milliliters, or 5 liters, or 0.5 liters of it. In fact, we can leave this as 500 milliliters. Well, how does this work? M1V1 equals M2V2. So we multiply those two and divide by the 12. We get this. 12 molar times V1 equals M2 times V2. Or V1 equals 3.0 molar times 0.5 liters over 12 molar, or 0.125 liters or 125 milliliters. Now, this could have been 500 the entire time, and we would have got the same thing. But we can keep going with this because we can do what's called a serial dilution. Now, a serial dilution is a series of dilution steps that manipulates the concentration from one that is very concentrated to one that is very dilute. And what will the final concentration be in this particular scenario that we have here, where we have 2.0 molar solution? We're going to take 1 milliliter of that, 1 milliliter of 2.0 molar solution. We're going to add it to 9 milliliters of this other thing. So that's going to be 2.0 times 1. We're going to put that in here. So now all of a sudden, this 2.0 times 1 equals, we'll call it 2 for right now. Okay, but that comes into here, and now all of a sudden we have 2 divided by 10 milliliters of stuff. All right, you see that? So we take 1 milliliter of stuff, and now we have this 2 moles, or 2 millimoles, and we divide it by 10. Okay, so now it's 0.2. Oh, my pen is not working. What is up with that? Again, not mine. This becomes, so we're take 2.0 millimole, which is like a milliliter times a mole, it's a millimole. Then come over here, and we're going to, now it's in 10 times the solution. So this is now 2 over 10, or 0.2 millimole. And we're going to take 1 milliliter of that, and we're going to into 9 milliliters of water. And this is another 1/10 dilution. See how we divided by 10 to get there? So we'll divide by 10 again. This will become 0.02 millimoles. And then we'll divide again, and this is going to become 0.002 mole. But then this time, instead of dividing by 10, we're going to divide by 1 plus 1, which is 2. And this is going to become 0.001 millimole. And so we diluted this by 10, 100, 1,000, 2,000 times. And so our molarity over here is 0.0002. I'm sorry, 0.001. No, I still messed that up. Is 1/1000 of a mole. 0.0001 mole per liter. We will do more of these in class. Take a look at these if you didn't get it, and go back through the process again and think about the 1 plus the 9. That equals 10 milliliters. And that is it for our notes for chapter 16. That was 16.1 and 16.2. And we'll see you guys next time. See you next time.